All right, well, thank you for letting me talk. Yeah, I want to tell you a little bit of a sort of quick story about infinite quivers and mutation sequences applied to them. And I'm going to specify, I really care about actually infinite mutation sequences. And so we're going to talk about that a little bit. I just want to say this is based on work that's on the archive as of a couple months ago, so feel free to go check that out. There's sort of a lot to it. Okay, so first of all, what are we talking about, right? For our purposes, a quiver is just going to mean something that's a directed multigraph, no loops, so no vertices with an arrow to itself, and no oriented two cycles. We've seen these in the cluster algebras talks we've already had today, so I feel good about this. I have a little bit of a short exact heuristic here, so I want you to think about quiver mutation as a local operation on quivers. There's a particular three-step algorithm that Amanda did show us, but just think about a local transformation on quivers. And then there's sort of this really important property of quiver mutations is that they're involutive. If you pick a vertex and you mutate there twice in a row, you're going to get back to where you started. Okay, why do we do these things? And really, I want to make the pitch for why do we think about quivers of infinite rank with infinitely many vertices. So there are plenty of examples of cluster combinatorics of infinite rank sort of arising in nature, so to speak. One example is infinite marked surfaces. So if you are familiar with the story about cluster algebras from triangulations of marked surfaces, there's nothing stopping you from putting infinitely many marked points on your boundary, right? So what happens when you try and triangulate such a surface, right? Well, you're going to have infinitely many arcs and you get an infinite quiver, right? But the combinatorics of quiver mutations remain the same. You can flip your arcs as usual, right? Things happen in the limit, but you can deal with infinite mutation sequences in this geometric way. You can also sort of abstractly think about cluster algebras of infinite rank as certain co-limits in a very certain category of finite rank cluster algebras. This is due to work of Sirogrotz in 2015. And more recently, as of last year, there's another instantiation of this in the case of the infinite Grassmannian, which I'll talk about in a second. I'll talk about it now. So you also have an infinite Grassmannian. This is sort of a very weird space. It's like infinite dimensional. It has a very strange sort of coordinate ring, but you can do all your familiar sort of cluster combinatorics in this thing. Sirogrotz and Christian Gorf last year sort of looked at the cluster structure on this, and they realized it as a co-limit in an appropriate sense of the cluster structures on coordinate rings of finite rank Grassmannians. You can also do some additive categorification stuff. You can look at plenty of representation theoretic ways of looking at cluster algebras. I've drawn another infinite surface here. It's actually sort of the same one. It's the disk with infinitely many marked points. This is work of a bunch of people, honestly. But you can look at like projective modules over the quiver here, and these correspond to certain summands of a cluster tilting object. And more recently, due to some work of Hernandez-Leclerc, and then a number of other people, Kang, Kashiwara, Kim, and Kashiwara, Kim, and Park, there's this monoidal categorification story for certain cluster algebras. They have finite rank stories, but they also have this really nice infinite rank story. You have an infinite quiver, and this is going to give you a cluster algebra that sort of densely embeds into the growth and decay of a certain monoidal category. So, okay, how are we going to do this? How are we going to set things up the right way? Right, so I'm going to take a topological approach. I'm going to define for you two spaces here, which I call AF and LF. And I'm going to say these are spaces whose points are quivers with vertex set the natural numbers, right? Arrow finite quivers, I'll take to mean between any two vertices, there are only finitely many arrows. Could be zero, right? But only finitely many. I'm never going to have infinitely many arrows from one vertex to another. And locally finite will be something stronger. Of course, this will imply arrow finite, but what I really am going to require here is that the degree of every vertex is finite. Okay, so as an example, here's a locally finite quiver, right? I take this sort of type A infinity quiver, and just for fun, I've doubled the arrow weights every time I go to the right. I've got powers of 2 here. This is a locally finite quiver. Here's another example of an arrow finite quiver, but at least if you believe my dots, this is not a locally finite quiver. I've got vertices like 1 and 2 of infinite degree. Okay, and so what am I going to do here to define these topologies I talked about, right? I'm going to talk about quivers that sort of look like my quiver on a given large full subquiver. So formally, you pick some finite set of natural numbers. Typically, you want to think about this as being kind of large, and you collect all the quivers Q prime, which agree with your quiver Q on that full subquiver induced by those vertices. You can do a similar story. I'm going to define this other set W. I'm tweaking one thing. I'm saying they're over full subquivers on this vertex set agree. I put a definition here. It's a little bit stronger. I don't really want to get into that now, but you can get a different topology out of this. And so here's a proposition for you. These sets form bases for topology on your space AF. Right? Moreover, the W topology, the one with the over full subquivers that I haven't told you about, is strictly finer than the U topology. And so you have these spaces AF weak and AF strong. Same underlying set, different topologies. Another proposition that's kind of nice here is that the mutation map is actually continuous. And since it's a continuous bijection and it's got a continuous inverse, namely itself, it's a homeomorphism. So it's kind of nice to get a continuous group action of the countable infinite rank universal Coxeter group on your space. Okay, for two of these spaces, the weak topology on the whole space AF and the strong topology on the subspace LF, you get this really nice space called the Baire space. This is the space of infinite sequences of natural numbers. If you don't really like thinking about product topologies, this is homeomorphic to the space of irrational numbers between 0 and 1, though not in any like nice symmetric way or anything. And also the sort of cross terms in that square, if you want to think of it like that, are not even close to being this kind of space. Formally, they're not Polish spaces. They have some bad topological features. Okay, what else can you say in this framework once you've set up all this topology? Okay, well, you can talk about properties of quivers as subspaces of these guys. I can look at the subspace of AF of all acyclic quivers, for example. What does that look like? Right? Turns out that's a closed set. Right? It's got empty interior, it's not dense. So you can say things like this. You can talk about infinite mutation sequence convergence and divergence. Now that you have a topology, when you have an infinite sequence of points, you can look at where it converges, if it does. Right? And so I provide a complete characterization in the strong topology on LF, for example, based on combinatorial properties of an infinite mutation sequence, when it has a dense domain of convergence and a dense domain of divergence. You can also look at really special infinite quivers. There's this really special infinite quiver I like that I've been calling the Freycinet quiver. This comes from a construction in model theory from mathematical logic. It's this really nice symmetric infinite quiver that when you mutate it, you actually get something isomorphic to what you started with, but it's also sort of flexible in that you can use it to approximate any finite quiver you want. So I want to spend just the last little bit here talking about what this sort of looks like. Right? So sort of the takeaway I want you to get is that these infinite mutation sequences can be really finicky. Things can be really fragile. Right? If I take this infinite mutation sequence 1, 2, 3, 4, 5, and so on, right? And I start with these three pretty similar looking quivers. Okay, I do a few steps, right? There's my mutation at 1, there's my mutation at 2, there's my mutation at 3, right? I sort of get something in this first case where I'm just doing sinc source mutations. In the second case, I'm sort of looking at a triangle moving to the right. And in the third case, I get something that degenerates to the second case. And so you see, you can have things converge in the weak and strong topology, just the weak topology, not the strong topology. And as it turns out, you can have things that are pretty close to your original guide that don't converge in either. And so that's what I wanted to say. I guess, okay. Well, that's what I wanted to say. So thank you.
We have a question for Benjamin. Well, I have a question. So does it say like anything you say about the like Gratz court work on this Sato-Grassmannian?
Yeah, they look at the Sato-Grassmannian. They look at like the sort of connected component where your subspaces have virtual dimension 0, and they're kind of just focusing on that. Yeah. But yeah, that's the space that they use.
Okay. All right. Thank you.